It is some system that interacts with the quantum field locally and that thus is able to exchange quanta with the field. The Unruh effect in this context can be thought of as an accelerated detector will reach a thermal state after interacting with Minkowski's vacuum for long enough time. So that was the introduction, and then now we're going to start with mathematics and with the concrete models I'm going to propose. So first of all, what kind of fields are we going to be dealing with here? We're going to deal with a real scalar Klein-Gordon field in a globally hyperbolic spacetime in 3+1 dimensions, which has these equations of motion and whose classical equations of motion in their inhomogeneous version are given by the same with a scalar, not an operator value, like a function, and some sorts f. So this equation admits an advanced and a retarded solution, such as you can write them down with an integral kernel of this form, and the advanced solution is the unique solution to this equation whose support lies entirely on the path of the support of f, and similarly, the retarded solution is a map that takes any function and takes it to a solution of this equation such that the support of this solution is in the causal future of the support of the function f. Also, these operators are unique in such a way that basically inverting the arguments gives you, inverts whether you have the retarded or the advanced solution. So this is what we understand as a free quantum field. When we put together also the requirement that the field fulfills the so-called canonical commutation relations. That is, the field has to be thought of as an operator or an element of an algebra that is takes functions, let's say, and gives you operators. And in this distributional form, the commutator of the field in two spacetime points has to be proportional to the identity and to these classical advanced and retarded propagators. So this is like a covariant version of what we all know, that the Q and P commute to I. So what does one calculate always in the context of detector models? So in a detector model, you have a bunch of systems with operators J that all couple in different regions, possibly, to the quantum field. And what one is interested in is into calculating the, let's say, unitary evolution of the joint system. And we do that through, in the interaction picture, through this so-called scattering operator. So there are two things that people have done. One is to, there are many ways of thinking about this, but the most ecumenic way is to think that we're thinking about the interaction as a channel over the detector. That is, we have an initial density matrix for the detector, and the interaction with the field implements a channel that depends, of course, on the initial state of the field. On the other hand, one can do something that has come up later, and I don't know, from the 2020s, is to calculate induced observables. That is, if I have an observable of the detector, I can envision a map that takes observables of the detector to observables of the field in such a way that when I measure something about the detector, I'm measuring something about the quantum field after the interaction, right? And it's given by this expression, formal. All these are formal expressions. In case you're mathematically inclined, they also hold in the case of, perhaps with some subtleties, when one extends these notions to systems that don't have a description in terms of density matrix, and so on and so forth. So what are the common approaches? The first one is to say that we have, where we do perturbation theory. So every time you see something like this, of, okay, we calculate this thing at second order in perturbation theory, basically what you're saying is that your channel is the identity channel plus some perturbation that I'm calling here theta. I won't use it again, so forget about it. Then there's also, there's been attempts. I'm not putting references, but there are many papers in which one tries to think about this thing in the Nakajima-Svansek way of thinking about it as some sort of master equation in the weak coupling regime that gives you finite answers. That is, they're not perturbative, but they're evaluated in a coarse grain time. That is, well, we can go through it later. Then there's all this idea of doing Gaussian operations. There are many works on this business. One discretizes the field, right? One starts with a Gaussian state for the detector, that in that case has to be thought of as a harmonic oscillator. And one just solves the Gaussian equations of motion that are basically for the covariance metrics for many modes and tries to say something about the system, right? So the first approach yields potentially covariant expressions. That is, one can make this guy here covariant in a very particular sense. And the second is a coarse grain, in a way. So like for this equation to represent the actual dynamics of what's going on, you really need to wait a long time. And you have to define things in a time scale that is much larger than any other scale of your system, right? And there is a problem because you're trying to do things locally and covariantly. So if you have a system that follows this kind of thing, obviously you're preferring, you have an observer for which that is true, and then your whole theory and your predictions are not covariant anymore. So, but then you would say, okay, so this is the reason why many people use this thing. Because, well, you can actually make covariant statements with it. But it's a problem because this is a perturbation. So for many things, you cannot use this thing. And it's very intuitive why you cannot. For instance, we will see later that if I wanted to use this kind of method to calculate Bell inequalities, I'm not going to be able to. Because this method is never going to yield observables that are bounded, even though you started with a bounded operator. So like you cannot use it for that. Also, we will see that for things like measuring whether the initial state of the field was Gaussian, you're not going to be able to use that method because we're going to see that this kind of thing, at the lowest order at least, cannot tell apart Gaussian states from non-Gaussian states. So, by the way, how much time I have? Because this can go forever. Like 1 hour. 1 hour. So let me talk a little bit also, because I've been talking about covariance and methods, but then even for detector models, in which one calculates things like this may not be covariant. So in this little work here that we have with Maria and with Eduardo Martinez from the University of Waterloo back in the day, what we saw is that imposing at the level of the currents that are associated with the detectors, that these also satisfy the macrocausality condition, that is that the commute in space-like separation is a necessary and sufficient condition for the statistics or like the predictions of the model at the level of perturbation theory to not incur in superluminal signaling and valuations of causality. Go for it. Oh. I'm very sorry. I'm so very sorry. It's the commutator of x, the j evaluated at x with j evaluated at y. So basically, that this thing has to behave like a field. That's the point. Is that the only option? So basically, what we concluded from this work is that you have 3 options here. One is J is a quantum field. Seems reasonable, right? Well, we'll see how reasonable it is later. Jx does not evolve. It's not as unreasonable as it would seem, and there are many models that account for this thing, and basically these are the kind of currents that generate quantum-controlled displacements. And I think here in this institute, they use this kind of thing a lot, so it's like not something to disregard that easily. But if you want to go a little bit further, what has to happen is that, well, the third option, that is, okay, this is 0 in space-like separation, because these J's don't have support in any 2 space-like separated points. So if we constrain J to live on a time-lag trajectory, the condition is also fulfilled. So that also, in principle, formally, doesn't give you superluminal signaling. And the predictions will be covariant and will be causal. The problem with the point-like limit here is that the point-like models are ill-defined mathematically. And you would say, but wait, I mean, well, I don't know how many articles on this thing have you read in your life, but they're mostly about that. So what's going on? More on that later. For the time being, let's focus on a particular model. There's the model I want to talk about today. There's the one that we propose that puts together many of the pieces. So imagine that I have a harmonic oscillator evolving along what I'm going to interpret as its own proper time that couples along a trajectory, z of tau, with a field amplitude. And the interaction is modulated by a time window that I'm calling here. So, of course, in order for this to be an interaction, unitary, or whatever you want to call it, I also have to have that the Klein-Gordon equation has this extra non-homogeneous term that depends on the detector. So this describes the interaction of the harmonic oscillator with the quantum field. Don't get scared by this expression. Let's look first at this one, right? Here I have the harmonic oscillator sourced by the field at a point. The inversion of the field equals the value of the detector is sourcing it, and it only, of course, it only happens at the point where the detector is. So this describes a detector that is always switched on and inertial at some position in space, x0. So this is a generalization of that. That is covariant. You can check that if you do the inertial trajectory and all that stuff, and you do it in Minkowski, and you plug this all those parameters in this expression, it gives you exactly this. This is just the current, let's say, that modulates the interaction along a trajectory. And well, we're also considering that the field could have a mass and could have a non-trivial coupling to gravity, all that kind of business. So, the reduced dynamics. So what are we going to do here? We're going to solve for phi. And we're going to solve for phi, writing it as a homogeneous solution to the Klein-Gordon, plus the retarded solution associated with this current here. This is something that is done all the time in open quantum systems. The only thing is that usually in open quantum systems, the Heisenberg equations of motion are not linear. But in this case, they are, so we can use the same method there. So if we substitute, well, okay, so one thing. Why are we using the retarded propagator? Because you could tell me that this is true for any propagator, right? I've been told this. I mean, if you don't use the retarded propagator, this is still true, but this homogeneous solution won't coincide with the free field in the path of the interaction. So this is actually the only solution such that the field is free, in a way, before the interaction happens. So it's the right way of solving that part of the equation. When we substitute back on the equation for the oscillator, we find the following. We find an integral differential equation for Q with some delay. There is causal because the retarded propagator is such that this will be 0 if S is larger than tau. It's local because it's modulated by this his here. And we see that doesn't depend on the state of the field. So we've completely separated a part that depends only on the detector and a part that depends only on the free field. So this guy here is like an interaction picture. And it acts as a source of a detector that evolves with non-local equations of motion. This, I don't know how surprising this is for you guys, perhaps not at all, but this is not something that happens at all unless you have a linear system. This is something that only happens here. If you had, even the stupidest of examples, a qubit interacting with a quantum field in a similar way, this cannot be split in this way. In fact, that there is a problem because in those kind of systems are extremely difficult to solve when they're made local. So there's not much we can do in the nonperturbative level. There is not this. Now let me talk about the need of renormalization here. So this happens with all these kind of distributions that you find in field theory, but I'm gonna constrain the analysis of the problem to this particular model. So if we consider the retarded propagator as a distribution of x and y, one can see that it has an ultraviolet divergence in the coincidence limit. Independently of the space-time you're dealing with, if you go to normal coordinates, very close to some point, and you start looking things around, the thing goes more or less like this. Where, if you know a little bit about these things, you will recognize that this is the retarded propagator of the Klein-Gordon field for a massless field in 3+1 dimensions. So it's a reasonable thing. It's like when I go very close, it starts looking like if it was a massless field. And if you don't like this kind of expression, you just can think about that this is delta of the difference of times minus delta, the difference of positions, that is the retarded time over the distance. That gives the kind of like linear Becher potentials that we see that have a fall-off of 1 over r, right? So it's not strange. However, we see that when, imagine that now I give you a trajectory such that delta of r is 0. Then I get delta of the difference of times over 0. That is a hand-wavy way of saying that this is not a distribution. It's not good. Doesn't work. If you want to look at it in another way, if you put trajectories of whatever kind, you can show actually that this goes like this, like the delta of the difference square, which is not a distribution either. So then there is, well, I have all this slide making this thing rigorous, but how much time do I have? 40 minutes. Perhaps I have time. Not with this, right? Okay. I'm sorry, I'm kind of useless in this thing, so I don't want to make a fool of myself. Could you? Okay. Okay, I will read this to you. So the statement that that is not a well-defined distribution in any spacetime can be actually made rigorous. So it's not a hand-wavy argument of how things go, more or less. That was just an explanation for you guys to know what's going on. So I won't bore you with the details. Well, that's not true. That's what I'm doing right now. So if you have a distribution in Rn overall, its singular support is the set of points in which it cannot be defined as a smooth function. That is, have a distribution. There are points, like, I don't know, you take a principal value, you take a delta, the points in which is singular. That's an intuitive definition, right? So there's this notion that one can refine the concept of singularity for distributions, right? And that is called the wavefront set. part of what what is called in mathematics the microlocal analysis. In that context, so if I take, let's say, a distribution, I can locally calculate this Fourier transform, let's say normal coordinates around any point, and I can check in which directions it doesn't decrease faster than any polynomial, right? For instance, the Fourier transform of a delta is 1, so it doesn't decay in any direction. So the wavefront set are those directions in which it doesn't decay, right? So the idea is that, okay, maybe you have heard a million times that, no, their two distributions cannot be multiplied. Well, that is not true. It is true if you refuse to think about the microlocal structure, what you're dealing with. So if you have two distributions, T and T prime, you can define their product actually through these Fourier transforms. That is, you convolute the Fourier transforms, and then if you get a distribution in the Fourier space, you can get back a distribution over the real space. So that's how you multiply distributions. But for the convolution to be well defined, the points in which these guys don't decay cannot have opposite directions, because then when I convolute, I would be integrating, I don't know, a polynomial against a polynomial. And then it just like blows up, because it blows up for all k, it's not a well-defined distribution. So what happens here is that the singular support of this kind of guy, that's what we're dealing with here. I omitted the metric and all that stuff because I don't care at this point. The wavefront set consists on, of course, the singular support are all the points that are in the trajectory, and the directions in which it doesn't decay, you can check, because of this thing of the delta I was telling before, that is in the perpendicular directions to the trajectory. So further, if you analyze what the retarded propagator is of a Klein-Gordon field in a globally hyperbolic spacetime, there's like a very detailed analysis of what you can do, because, of course, because it's all about the covariant derivatives and all that stuff. When you go very close to like points that are very close together, it starts looking like Klein-Gordon in Minkowski. And then, well, you basically can calculate this wavefront set. And it turns out that the points, this is going to be, because it's a distribution in x and y, is in R8. So basically, the singular support are the points in which these guys are related by like geodesic, and also the coincidence limit. We don't care about the points that are related by like geodesics, because those are not going to be a problem with this distribution, but the coincidence limit is. And that's the very deep, very mathematical reason why you cannot do this. It's a nice result, because that means that, like, okay, it's not a problem of your spacetime. It's a problem of there's like something very deep in the UV, something that you're asking for your theories that doesn't allow to take these point-like limits. And actually, this is something that also happens for any point-like interaction, not only for this model. The difference is that in this model, we're going to be able to renormalize at all orders. And that's going to give us a finite outcome. So there's this very pedantic way of doing renormalization. It's called the Epstein Glasser procedure. Well, I don't know who's listening in the internet. Maybe like I'm screwing myself here, but probably Epstein Glasser. So we understand renormalization as I have a distribution over a set that is not 0. There is Rn minus 0, anywhere there. And what I do is to characterize the possible extensions, mathematically, that I can have as a distribution to the whole Rn. Turns out that that's a very mathematical way of thinking about it, which in this context, there is a covariant theory. That's the way we should think about it, because we don't know anything. We don't have intuition about how the theory looks in the UV or anything. Basically, you demand that the extensions have certain particular behavior in the UV when you go to 0, then the amount of extensions is finite. That means that you can characterize all possible extensions. And in particular, what we studied here is using these tools is that any renormalization of this guy as a function of tau and s is some smooth kernel. Well, it doesn't have to be smooth, but it's integrable, times some arbitrary constant times the delta, times some other arbitrary constant times the delta prime, the derivative of the delta. So those are all the possible values that this thing can have. Let's stop for a moment and let's think what we're doing here. I have a singular interaction. I know that cannot be realistic because it's a point-like interaction. So you would tell me there's something going on there that you're just like missing it. So it turns out that, but it turns out that I don't want to know how that looks, because any attempt to do so would get me into a non-integrable system, a system with infinite degrees of freedom, whatever. I don't want to go there. I don't want a fine-grained explanation. So what this is telling you is that you don't need the fine-grained explanation. You have something like this. There is a nice kernel, times two things that you cannot predict with your model, but you can fix phenomenologically. Those are the outcomes of some measurement. So how would you take this? Okay, so if I have this detector that is pointlike or whatever, where am I going to see? Well, so in principle, when the detector is very small, what the theory, without the bare theory, is telling you is that there are going to be very important effects coming from the UV. But you don't know exactly how that's going to play out. So what you do is to assume that more or less there's something in the UV that is conjuring such that everything is well-defined. And the amount of numbers that you need to fix to have that well-defined model is just 2. So it's not that different from specifying a model from a Hamiltonian in that sense, because in a Hamiltonian you also put just a bunch of parameters. So if we introduce and interpret those parameters in terms of things that enter the equation, what we have is something like this. This guy here is a smooth kernel. Now we don't have any, it's still causal. We don't have any problem with the well-definedness in terms of renormalization, divergence, or whatsoever. We have a shifted time-dependent frequency, and we have a dissipation term that are related with the two phenomenological constants that we had at the beginning. So here, this time-dependent dissipation term is basically the square of the window function times the phenomenological constant that was associated with the derivative coupling. And this time-dependent frequency is the original frequency plus these two terms that basically create this time dependence. So it's like, in a way, it's like a lamp shift, if you're familiar with that. A time-dependent lamp shift. Okay, now you can breathe. Those were the mathematics. I'm not going to spit more terms that, you just cannot know if you've not seen them before, this talk. Now we're going to talk about the general solution, and we're going to talk about the induced observables in this model. Go for it. Yes, I just changing the name.
Okay, right. So to give a more concrete physical.
Yeah, exactly. It's because if you look at the literature on these things, they always call gamma the dissipation constant, right? So it's like it gives them the flavor that that's what they mean.
Okay, just wanted to make sure that
Yeah, no,
special is happening.
nothing special is happening, no. Well, I mean, perhaps that they're modulated. That's not that common. And that also the modulation is given by the square of the say the switching function that you have, and that's what makes it local. So you see, the shift only happens when the detector is on. The dissipation only happens when the detector is on. That's not that common to see in the literature, at least. So, okay. So the equation is non-Markovian because it has a memory kernel. And that is not surprising because we have an open quantum system, right? And the non-perturbative level. And we're not making any approximations here. So far, this is exact. With renormalized, but we've not approximated anything. That's what I want to say. So it has, of course, because it's an open quantum system that is interacting with a field, it has like a backflow of information. But doesn't depend on the state of the field. If you want an intuition for that, is that this is a linear system and there's a superposition principle behind the curtain. So whatever the detector does, that comes back to itself cannot depend on the state of the field, because there you have waves that just pass through each other without seeing each other. So because it's a linear equation, the general solution of the reduced dynamics still something of this kind, where you have a homogeneous solution and a particular solution. The homogeneous solution acts only on the degrees of freedom of the detector, and the particular solution acts only on the degrees of freedom of the field. Here, where I'm defining as this small phi is just this mere field amplitude along the trajectory, where this guy here is the fundamental solution associated with the integral differential equation, that under some general conditions is something that still exists, even if the equation is integral differential. It has to do with things like the Fredholm alternative and stuff like that, if you're into that. Yeah. So this has a fundamental solution and a homogeneous solution. Okay, sorry. A propagator. Something that you integrate it against, and for everything here, it's like an integral kernel that for anything that you put here gives you a solution. So that's a particular solution. Because it's linear, it's on functions, but it's also on operators, because it doesn't involve multiplication of things. Yeah, I mean, that's what makes all this thing is essentially classical. We will get to something quantum when we want to do measurements. That's the point. But we want all the dynamics to be classical because, things are complicated enough the way they are, as you can guess. So, yes. So we have this guy here. And this is the fundamental solution of the integral differential equation, or like the green function of the integral differential equation, and is modulated by this guy. So we see that this is a field amplitude that is mirrored in this region. So if you're into quantum field theory, that we say that it's localized in the interaction region, or localizable in the interaction region, or in the causal hull of the trajectory, within the support of the window function. That's what that is. So it's something kind of that is in the interaction region. Also note that when tau grows bigger than the support of chi, this stops depending on tau anymore. That will be important later. So, I told you I wouldn't say wavefront set again, but I'm just going to repeat it one last time. So the theory of wavefront sets can be extended to operator value distributions, such as the field. But the sense in which this guy is an operator, we've not said anything yet about the Hilbert space of the field. It depends on the representation, which in turn depends on which state you're using to construct the representation in which it lives as an operator, right? So turns out that there's a class of states called the Hadamard states, for which the wavefront set of these distributions can be characterized in full. And basically those are if you want to think about them as the things that look like a free field when you go to very high energies. Same story as always. So in the other case, with the propagators, we didn't have that problem because that's a classical quantity that is fixed. Here, we could choose a state that has more singularities than the propagators. And in that case, well, we would run into a problem trying to do these kind of things. There would be things like that maybe wouldn't be well defined. But in this case, for any Hadamard state, we build a Hilbert space in which this phi lives and has a wavefront set that, well, is only about light-like directions. And because this guy here only has like a wavefront set that only lives in space-like directions, we can multiply them, and basically we can get phi. All this to tell you this guy is okay. It's an operator. For any Hadamard representation of the field, you measure with this detector and you get a well-defined operator. That will have its spectra, well, it will be closable, it will have it will be essentially self-adjoint, it will have all the properties that we demand from that. So intuitively, yes, if you want to know what this guy is, because maybe you don't have a good intuition, it's just a damping term plus some oscillating thing. That's because it is modulated by an oscillation. The reason why is, well, it's because it's a damped harmonic oscillator with time-dependent parameters. But still, that has always a very intuitive behavior, even though the analytic solutions are never known, because even the Matthew equation is already a mess. But if you check the steps that we took, we've taken a very complicated problem, and we pushed all the complexity in this kind of business of solving non-autonomous that are called harmonic oscillators, which is something that is way more tractable. And because we know that this guy is well-defined, we can treat this thing numerically and say that if a function kind of resembles chi or kind of resembles r, because we're doing something with numerics, then we can calculate this thing to a good approximation. That's part also of the motivation of this work. Because if you were not doing it with a system that is as simple as this, you wouldn't have a good notion of covariance to be able to do numerics with it. So far, so good? Questions? How much time do I have left? Oh, okay, sorry. But I don't, okay. Okay, perfect. So now we start with induced observables and stuff like that. So okay, I measured something that has to do with the detector, with the Q. What does that tell me about the field? So, well, for this quadrature, if you want, all the information is encoded in the characteristic function. So where the averages are taking the Heisenberg picture. So if we start with an uncorrelated state before the interaction, it is clear that as Q evolves in the Heisenberg picture, what I actually get is this. Is that clear? Where this is the average in the initial state of the detector, and this is the average in the state of the field. Of this particular field amplitude. And now, the beautiful thing about this system is that this guy obeys this integral differential equation that is generally dissipative. So these solutions, even though they're operator valued, they decay with time. Decay to 0. That means that we have this nice notion that if the interaction is wide enough, this Q0 goes to 0, and the characteristic function of the Q as time goes becomes the characteristic function in the initial state of the field of this particular field amplitude. So this is the sense in which we're talking about pointer variables. The Q starts interacting with the field and eventually starts keeping track of this distinguished field amplitude. And any reading of this Q basically mimics the one of that field amplitude. It is a perfect measurement of that particular smear field amplitude. More generally, if we don't want to wait that long, if f is any function, you can use Fourier analysis to show that the average of any function of the quadrature at time tau is given by the same function convoluted or convolved. How do you say in English? Convoluted. With this particular function, that depends on the initial state of the detector. If you want, if this was a Gaussian initial state, like the ground state of a thermal state, this would give you a Gaussian also. So it would be like a Gaussian filter of what you put in the beginning. And this is a very concrete sense in which you get this. So if you recall our definition of induced observables, all these dynamics end up giving you this nice characterization. That is that I input the observable induced on the field by any function of Q is this convolution. And this, for Hadamard representation, all that stuff is something that converges in the widest of senses. This is an actual equation. It's not, and there's no approximation there. And something that will be important later is that because H is a probability distribution, because the Fourier transform of a characteristic function, then we can use Young's inequality. There's some set of inequalities about LP spaces and convolutions to see that this actually decreases the infinite norm of F, the supremum norm. And if you check the the functional calculus, what that means is that this map is norm decreasing. This can be shown in more general terms, but I thought it was, if you know this couple of pieces, I thought it was nice to see it just from here. Okay, one last thing I wanted to tell you about this is like, okay, so we're dealing with a system of an integral differential equation that with non-autonomous terms or whatsoever, and it has to have a memory kernel, I've been telling you, because the system is an open system, there is no Markovian. So something that you cannot see unless you do things fully relativistically is that there is a way of getting a Markovian evolution non-perturbatively. And the reason is the following. Imagine that I have this detector that is interacting with the quantum field along the trajectory, and I want to see more or less what the back reaction is. So the detector interacts with the field, information escapes at the speed of light. That only happens if Huygens principle is satisfied, and doesn't come back. So that is something that you cannot not understand in non-relativistic terms, but that holds here. So you have a point-like interaction that in a system that satisfies the Huygens principle, that evolution has to be Markovian. Of course, if I had a mass term, there could be back reactions because particles or like wavelets or whatever don't travel at the speed of light. If I was in a curved space-time, there's also back reaction because the light back reacts on gravity also. If I had mirrors, this wouldn't happen either. But in any case, if I have massless fields, in Minkowski, I get a damped harmonic oscillator with a source term. And that solves the system non-perturbatively. I see you looking. It's okay. In fact, well, you can, in this sense, you can, in this setup, you can solve the system exactly. Well, not exactly. You can parameterize it, saying that you have the homogeneous solution is a damping term that can be calculated exactly. Plus, these guys are some solutions that are, how do you call it? They preserve some kind of like Wronskian. So you can think about them as some plane waves, but with some time-dependent frequency. Are the typical solutions that you get when you have a harmonic oscillator with a time-dependent frequency. But you see, we're even taking out this part that was the important one because it's the ones that they kind of like dumps the solution well enough. So like it changes the localization of the thing, right? And also, something that is non-trivial in non-local equations within memory kernels is to find the fundamental solution. And in this case, we can. For systems that are non-local, it's not clear that you can get a closed expression for the retarded propagator. So, but in this case, we can. So that means that we can get the exact form of the induced observables, at least up to how accurately we want to simulate U, which is nice. Remember, all this is non-perturbative. And we now go to the applications. So the cumulants of us, this is something that I'm defining here, don't jump on me. The cumulants of a state with respect to an observable are defined by me as the characteristic function of this guy. It's more or less like a classical thing. It's not any kind of a characteristic function that I'm defining in the quantum sense. So if I take the logarithm and then I do a power series, I get these numbers. So Gaussian states are, for systems that fulfill the canonical commutation relations, systems for which all the cumulants are 0 for n greater than 2. That this guy here is a Gaussian. That's the reason why they're called Gaussian. Non-Gaussian states are not exotic. If I flip a coin, that's not a Gaussian state. But why do we care about that? Because when we do thermodynamic assumptions about a system, and for instance, we're saying that we are in the ground state of something, if you have a field theory, the state is Gaussian if and only if it's free. So with those extra assumptions, that justify the interest in trying to see whether one can detect non-Gaussianities, at least locally, right? So this is something that cannot be seen at the lowest order in perturbation theory, as I was saying before. Perhaps you can go further in perturbations. But I think it's more natural to just take a model as simple as this and check how the higher order cumulants of the field potentially propagate to the detector after the interaction. And in fact, in this case, it's transparent. All the cumulants after the interaction of this quadrature are given by the quadratures of the field in the initial state. In the paper, actually, we calculated this with a one-particle state. There is no Gaussian to see how that goes. But I mean, there's no noise coming from if you start with a Gaussian state for the detector, basically that doesn't bother you because all the higher order cumulants just like pass through and don't see this first cumulant. There's no noise coming from the initial state of the detector. So it's like a very clean measurement of this. If you have very clean measurements of cumulants for these distributions, you will have very clean measurements of non-Gaussianity for the field after the interaction. That's another phenomenon that can only be seen in this kind of setup. And, well, I think I can go a little bit fast on this and just finish. Part of the motivation of all this business is try to do things with more detectors, right? Because then you can discuss correlations, and you can discuss entanglement harvesting, and you can discuss communication tasks. So when you do the same thing, you have to take into account several things. You have n detectors. Each of them has its own proper time, because they're following different trajectories, relativistically. They have their own parameters, because nothing tells you that renormalization is something independent on the detector that you're picking. And but the kernel will be this kernel actually changes because it's defined over, no, this one doesn't change because it's for each detector its own internal kernel of its own self-dynamics, let's say. We have for each of them, we have a similar source term. And then we have the interaction terms between the detectors. These terms here are the ones that dictate how detectors interact with each other. And basically, you can recognize that this is the linear Beaker potential generated by this source acting over the other detector. So this guy here, because it doesn't involve the coincidence limit, unless we want, but we don't want, doesn't need renormalization. It's well defined. You can do the same analysis with it before, but the problem there was always the coincidence limit. It was never the divergences that it has just because. And note that because we have a retarded propagator here, and these localized switching functions, all this interaction between the detectors, though retarded, is local. That is, if I have a detector I, That is, the only Qj influencing the dynamics of detector Qi are those whose trajectories intersect its causal path. So there's no causal phenomena here in the communication, as far as the communication between the detectors is concerned. And further, if I have that all the detectors are space-like separated, then I get the same equation that I had for each of the detectors separately. Each of the solutions in the space-like separated case is just given by the same thing, the homogeneous solution plus some phi i's, where all the phi i's are localizable in space-like separation and therefore independent observables of the field. And this implies, from the point of view of induced observables, that if one has an arrangement of n detectors in space-like separation, one can perform a set of measurements of functions fi such that this happens. That is, it takes two products of independent detectors to product of commuting fields. And further, because the norms of the operators are under control, if one measures some Bell inequality in these guys, and it follows all the steps back, one realizes that any violation of a Bell inequality in these guys implies a violation of a Bell inequality here. I'm not supposing that we have the CHSH, but that's what we had in mind. I guess one can have others. So let me conclude. So detector models play a more fundamental role in relativistic quantum physics because operations have to be implemented causally and locally. If one wants to probe non-trivial features of the field, one has to choose between causality violation interactions, ill-defined interactions, of intractable interactions at the nonperturbative level. However, our model, that is based on fully covariant and local Gaussian interaction, tackles the second issue by using rigorous renormalization techniques. This allows us to discuss measurements of non-Gaussianity and Bell inequalities. We discussed the non-Gaussianity. The Bell inequalities are work in progress. So in the future, we would like to know what is the role of gravity in all this, because basically all this kind of business is something that you would have in a flat background. And we would like to discuss, issues that have to do with thermalization of these guys. And with that, let me thank you. And please, if you have any questions.
At some point, you noted that the system is dissipative and expressed that Q0 goes to 0. Can you explain that again, why it's dissipative and if you use that somewhere?
Okay, I didn't use it anywhere. Okay, so you would agree that the damped harmonic oscillator is dissipative in the sense that the solutions go to 0, right? Yeah. So I guess your doubt is, okay, what if, there I have a time-dependent dissipation term, right? So it is in the paper. I don't know how to do that from the top of my head, but you can do by defining that P that I was defining after, you can define this, and the solutions overall take some form like, they're always modulated by something like this, which is something that you can do with a change of variables. I think it's something like this. And that modulates the whole solution. So, and what is not that solution is something that is bounded. So because this guy, if you remember, it was C2 more or less times chi square of tau, when I do this thing very wide, this thing goes to 0. So that means that those solutions, you can show that they go to 0 for very wide window functions. So that's the mathematical way of saying it. But the physical way is that, okay, these are systems that have dissipation. No problem.
Can you say more about covariance, actually?
About covariance. Okay, so at no point I used any foliation, and all the quantities that are calculated are based on functions in which I'm not telling you which coordinates I'm writing them. So no observable here depends on that choice, at least after the interaction. That's as far as covariance goes. I mean, that is clear from the first equation in that case. But that was mainly the effort of writing that down, is to say, okay, I have this function of this parameter, which is the proper time of the detector, and all the sources are things that are coordinate free. So in that case, well, okay, maybe for a calculation, you use some particular set of coordinates, but there's nothing about the calculation. Any two observers describing the system will get the same results in that way, I would say. So like the switching function is a scalar. Yeah, but that is covariant in the sense that you're saying that you have a window function there. That there's nothing non-covariant about it. It's a function on the manifold. Okay, yeah, no problem.